In our next question, we're going to discuss a better approach for summarizing a data set. This question is called, "Excuse me, I'm having a skewed moment." In this question, we're going to talk about how we can more precisely describe a large data set using summary statistics beyond just the mean, the median, or the mode, looking at things like the variance, the skew, and the kurtosis. And we're going to try and develop an intuitive sense of what these statistics really physically mean. Let's start off. If we take our data set, we can compute things like the mean very easily in NumPy. We can compute the variance. We can compute the standard deviation. We can compute the skew. We can compute the kurtosis if we import from SciPy. And we may have even relied on these before. We say, if we're going to compute a median, we might as well compute the variance and the standard deviation. And there's some implicit meaning behind these. We might rarely reach for things like the skew and the kurtosis. But think about what our value proposition from computing these are, what our motivation is. Our motivation is, can we find not one single scalar value, but a collection of scalar values that describe something interesting and meaningful about this large data set, so we don't have to tell somebody, oh, it's a billion points, point 1 is here, point 2 is here, point 3 is here, point 4 is here, which is not an efficient way for us to describe these large data sets. However, our intuition for what these statistics may mean is somewhat limited. And so, let me share with you a little bit of a starting point for an intuition of what these are. We know from a calculation perspective how to compute the mean. This is something that we do all the time. And so if we have a bunch of data sets, we say we just sum up all the values, we figure out how many total values are, and we divide it by the number of total values, and that gives us the mean. And you can see two parallel computations for the mean, one directly using the .mean API and one computed manually. If we want to compute the variance, we may or may not remember how we go about computing the variance. And when we compute the variance, what we're going to do is we're going to take each value and we're going to look at how far away it is from the mean. So we'll take each value and we'll subtract the mean from it. And because we want some notion of the magnitude of this distance, so that we want it to be the case that large magnitude of distance counts, but that if you have a positive distance and a negative distance that are symmetrical, they don't count. They don't negate each other. What we'll do is we'll square this. And then we'll sum this up and we'll divide this by the total number of values, and this computes the variance for us. And if we took a look at these two parallel computations of their variance, we'll see broadly the same answer. However, here's the, and let's also grab this down here. Just make sure we can view this. Perfect. Now, if we take a look at this formulation, we might notice that we're doing a sum and a length. So we could think of the variance as a sort of mean, or meaning the average distance from meaning to get the average distance from the central point, where we're looking at that distance squared. And one thing that pops up kind of interesting is, if we were to take a look at the units, if this were a physical quantity like heights or distances, something that we had measured, we're to take a look at the units here. Clearly, the units of the underlying data is meters. So we could say, oh, the mean is 4.95. The data is centered around 4.95 meters. If we were to take a look at the variance, one of the unfortunate things about the variance is the units are kind of dodgy. It's meters squared. And if we're thinking about a linear measurement, and we're saying, oh, the variance is a summary statistic for this linear measurement, but it's in area terms, that becomes a little bit tricky for us to understand. And so this leads us to an intuition for why we might want the standard deviation. The standard deviation is merely, let's take the variance and let's just take the square root of the variance. And when we take the square root of the variance, we get more reasonable units. We can say, well, some notion of the distance from that mean is 0.98 meters. And here we can see a very simple intuition for the standard deviation. The standard deviation and the variance are computing for us what's the spread of the distribution. Is it clustered around the mean, or is it really far away from the mean? And this starts to give us a little bit more information about where that data set looks. And so if we give somebody both the mean and the standard deviation, they broadly know, okay, the average value is about here, and most values are very close to that, or most values are very spread out. Because the variance is computing what is this distance from this mean, the standard deviation is just giving that to you in more reasonable units. Now, there is another formulation for the variance that we won't get into, that we may get into if we do talk about expectations and probabilities a little bit more. But there's a second formulation for the variance here, where we're looking at the squared values and the mean of the squared values minus the square of the mean of the values, although I don't know that that gives us a particular intuition at this particular point. We're not quite ready to get a good intuition for what the skew and the kurtosis are, but what I want to show you is mechanically what's going on with the skew and the kurtosis. The skew is what happens when, or is computed when, we try and figure out what the distance from the mean is. We divide that distance from the mean by the standard deviation. So we say, what is the number of standard deviations you are from the mean? We raise that to the third power, and we get the average of that. And one interesting thing you can see here is the skew is dimensionless. It doesn't have units. It's a ratio. It's a ratio of how many standard deviations the average value is from the mean raised to this third power. And this third power, what does that even really kind of mean? That's a little bit dodgy. If we think about what the kurtosis is about, it's a very similar formulation to the skew, but we're raising to the fourth power. And if we're not sure why we're raising to the third power, I'm pretty certain it's going to be a little bit tricky for us to understand why we might raise to the fourth power. But we will provide you an intuition in just a moment. I want to bring all of these definitions together to show you a little bit of terminology that will come up a couple of times and will come up every time you talk about these summary statistics. We can talk about the kurtosis, the skew, the variance, and the mean in terms of things like moments, raw moments, central moments, standardized moments. And so here we can see this is our computation for the kurtosis, and the computation for the skew is the exact same computation, except instead of the fourth power, it's the third power. We can see that the variance is part of this computation. We didn't divide by the standard deviation, and we raised everything to the second power. And you can think that here, and by the way, this is mislabeled, you can think here that the mean is another portion of this computation, but it's removing the subtraction of the mean here, and it's raising everything to the first power. One thing that we can say is that the mean, the variance, the skew, and the kurtosis are all summary statistics that represent moments and different powers of moments. The first moment, the second moment, the third, and the fourth moment. The first moment being a raw moment, meaning we're not demeaning it because that wouldn't be particularly meaningful. The second moment, the variance, being a central moment, we're demeaning it. We're trying to figure out how you are rotating around something at some central point, or how you are located around some central point, I should say. The skew and the kurtosis being standardized central moments. So we figure out how you are distributed around a central point, and then we standardize it to figure out that spread in terms of a number of standard deviations. And you can see this gives us a little bit of a sense for these. If we're to go back to our description, I want to just make sure that we see how this terminology lines up, because I find that the terminology, when you're seeing it for the first time, can be very confusing. We talk about the mean as a raw moment. We can talk about a moment around 0, which would just be every value and its distance from 0 and the mean of that. We could talk about the moment around the mean. And we can think that the mean is the first moment around the mean. Sorry, the first moment around 0. We can talk about an nth moment around the mean. And this is what we're talking about largely when we're talking about the skew and the kurtosis, minus this discussion of the standardization. The variance we can talk about as being the second moment around the mean. It's the squared distance from the mean and the mean of that. The standard deviation we can talk about as the square root of that second moment around the mean. And these standardized moments we can talk about as dividing by the standard deviation as part of our formulation. And so one thing that'll come up a little bit later is the first standard central moment of any distribution is always 0. The second standard central moment of any distribution is always 1. It does not matter what the data looks like. And this is just a consequence of these formulations and a consequence of how we're presenting this vocabulary. And we can see this if we look at an actual data set and we compute these. It doesn't matter what this data set is. It doesn't matter what's contained within. These will always be 0 and 1. And the reason for that is, and this is why when we talk about the mean, we're talking about not a standardized central moment. It wouldn't be very useful. When we talk about the variance, we don't talk about a standardized central moment. It wouldn't be particularly useful because it would always be 0 or 1. And this is why you see that asymmetry before, because as a consequence of the formulation, it's not particularly useful to talk about standardized central first and second moments, it is interesting to talk about non-standardized central moments, non-standardized second central moments, and raw first moments. And I put a little bit of the algebra here, but we won't go through it in too much depth. It's in the notes for you to review. Now, I've said the word moment many times, and I want to give you an intuition for what all of this really means. If you learn the term moment in the field of physics, you'll learn it in terms of some measurement, some calculation that is a product of a distance and some measurement of a physical quantity. And the idea here is we're trying to give a sense for how these things are located or distributed in space. And so we can think about something like the center of mass. When we did our last physics class, we remembered that we can model things as points, point masses at the center of mass. And so we have all sorts of weights orientated around in space, and we want to figure out, well, where is that center of mass? Where is the average point where we can see the representative mass of this object is? And this is what our first raw moment is. This is what the mean is. Mean is a measure of our center of mass. It's a physical quantity. When we talk about this from a physical perspective, we can also talk about what the rotational inertia of a piece of a physical entity is. You can think that if the mean is where all those weights are located and where the average point where those weights are located in space, you can think that if we have a bunch of points out to the edges, well, that's going to make it easier or harder for us to rotate this thing. Think about it. If you have a bunch of things clustered toward the center, you can spin it really fast, and it doesn't provide a lot of inertia against that desire to cause it to spin. But if you have them really spread out, then it has a particular rotational inertia. And you can imagine that it makes it a lot harder for you to move this thing rotationally. Well, it turns out that rotational inertia is actually the same thing as your variance. It is your second central standard moment. In statistics, instead of talking about this in terms of these product of distances and measurement, because we want to talk about these higher order moments, what we're talking about is a quantitative measure related to the shape of the graph of the values. So anytime we're computing a mean, a variance, a standard deviation, a skew, or a kurtosis, what we're really trying to communicate to somebody is, I don't want to tell you every single point in this data set, but I want to tell you broadly how it's shaped. I want to tell you broadly where that center of mass is. I want to tell you broadly what the spread of this is. That would be the mean and the variance, or the mean and the standard deviation. And I want to tell you how the tails look. And I want to tell you how this thing leans. Let me show you what I mean. But as an aside, I want to do one small thing. When we've plotted these data sets, we plotted the data sets looking like this. And you can see that here, the y-axis corresponds to what the value is, and the x-axis is just which measurement we took. And so you can see we took 1,000 measurements, we observed 1,000 things in the real world, and these are the values that we saw. And plotting it like this is not particularly meaningful, and the particular organization of these values is also not particularly meaningful. You know, what constitutes the 800th captured value versus the 900th captured value doesn't mean anything. These aren't captured in a particular order. It's not a time series. We're just saying, oh, the third value is this, the fourth value is this, the fifth value is this. And so if we were to sort these values, it really wouldn't make much of a difference in terms of what the graph means, but it does make a significant difference in terms of what the graph looks like. We can start to see some really interesting patterns here. And we're just saying, you know what, I don't care if it's the 400 or 400 the first value, just sort them by what their value are and show me what the values look like, and you can begin to see something interesting. Now, I'm going to stop using this kind of plotting in order to represent the data set. And instead, what I want to do is I want to look at the distribution of the values, the probability that a value exists, the frequency with which a value exists in very simple terms. In other words, I want to look at my values. I want to figure out what are the unique values and how many times those unique values appear. And I want to plot a bar chart with those unique values and how many times they appear. And you can see here, I have, and let me just make sure I only have one bar chart. Okay, very good. Here, what you can see is I have a bar chart, and it's not a very nice looking bar chart, but you can see I have a nice little bar chart here, and where that x-axis previously represented which sample I have. Now what the x-axis represents is what the value is. So I had 8 values. I had 8 discrete values in this data set, 1, 2, 3, 4, 5, 6, 7, and 8. And I think I had 8 discrete values. And this y-axis represents the count. So you can see that value of around 6 appeared 10 times. Now, if this is a continuous distribution, you can imagine that each value's likelihood of appearing it's pretty unique. If you look at your watch, what's the probability of seeing 10:05 and 3 nanoseconds? Well, it's pretty low, but seeing 10:05, if you bucket it up to the minute, is pretty high. One thing you can think is we have this contention when we're looking at these kind of graphs between what happens with the discrete distributions and the continuous distributions. But in general, what I'm going to do, instead of printing this as a bar chart, so I'm going to print this as a histogram. I'm going to bin them. And this is effectively the same thing as what I would do if I were to take these values, bucket them using pandas cut, and plot them. And you can see largely these line up. So we're going to look at these in terms of the frequency with which they appear. Now, what I want to do for you is I want to show you, and I want to remind you what happens when we take the mean and we move things around. What I've done with this data set, I've taken every value in the data set and I increased it by 10. The mean doesn't change. The shape of the data set doesn't. Sorry, the mean does change. The mean increases by 10, but the shape of the data set doesn't change. And this is what we saw before. You can see the mean changed if we shift every value up, but the shape of the data set doesn't change. All that happened was this x-axis got moved over. And so this is one of our reasons why the mean is maybe an insufficient statistic for our purposes. In a very similar sense, if we take this data set, we demean it, we multiply it, and then we remean it, what we'll see is that the variance will change, but if we take a look at the data set, we'll see the shape of the data set doesn't change. All we've done is we've taken this x-axis and we've moved this x-axis, we spread this x-axis out a little bit. And so it's clear that we need something beyond just the mean and the variance, or the mean and the standard deviation, to describe this data set. What I want to do for you is I want to share with you what the skew and the kurtosis are all about. The skew, I can show you what it looks like, and then we can develop a little bit of intuition. The skew is a measure for how the distribution leans. Does it lean to the left or does it lean to the right? And so I'm going to show you 3 data sets. And for those 3 data sets, you can see visually, without even having to think about it, how these 3 data sets differ. But what I'm going to show you about these 3 data sets is these 3 data sets will have the same mean, but they are very different data sets. They all have the same mean, but look, one of them is leaning to the left, one of them is leaning to the right, and one of them is symmetrical around the center. This is what the skew represents. The skew is a dimensionless scalar value that tells you negative, oh, this thing leans to the right, positive, this thing leans to the left. And we can play a couple of games with moving this data set around. We can play the same games, like if we add values around the mean, what you can see here is, and let's turn off our plot for a second. So if we play a couple of values here, if we play a couple of games here, we add a couple of values around the mean and a couple of values way out in the outliers, we can actually force this data set to have exactly the same mean and broadly the same variance, but the skew won't change, or the skew will be meaningfully different because the shape of the data set is meaningfully different. One of these clearly leans in one direction, one of them clearly leans in the other direction, even though we force that mean and that variance to be the same. One of the things that we can identify is for distributions that are, or for finite distributions, it is the case that if we compute the mean, the variance, the skew, the kurtosis, whatever the 5th moment is, whatever the 6th moment is, all of those moments up to infinity, we can actually precisely, uniquely define that data set. And so the reason why people stop at the kurtosis is the kurtosis is usually enough. The mean, variance, skew, and kurtosis are usually enough to describe the data set and usually have a physical analog. But it is actually the case that all of these moments, all the way up to infinity, can precisely describe what's happening in that data set. And presumably, at some point, the 6th or 7th or 8th moment, we start to lose discriminating ability for a real data set. In practice, past the kurtosis, we really lose our ability to properly discriminate these data sets. Now, I want to give you a view for what this really means, and this is going to be a little bit mathematical. One of the interesting things about these summary statistics is I can compute them in some sort of superposition. What I can do is I can take all of the values and I can partition them. Look at all the values before the mean and all the values after the mean, and I can compute the skew and the kurtosis, not by jamming them into one big equation here, but by computing something that kind of looks like the skew on the left-hand lobe and something that looks like the skew on the right-hand lobe, and adding them and just scaling them by the probability of you being in the left-hand lobe or the frequency of you being in the right-hand lobe. Some scaling factor corresponding to the number of values. What you can see here is this formulation for the skew, where I compute the skew in two parts for the values under the mean and the values above the mean, is exactly equivalent to my other formulation for the skew. I can do the same thing for the kurtosis. I can actually compute the kurtosis as the kurtosis of the values under the mean and the kurtosis of the values above the mean, and combine those as a simple linear combination. Now, why I might want to do that might not be clear. It's kind of bizarre. But I found this, when I discovered this intuition, reading through Stack Overflow, I found this a very powerful way to give a sense for what these things really mean beyond our standard way to describe it. One other little mathematical trick that I can do is if I think about what my formulation is. This is my general formulation for each one of the sides. I take the side, I demean it, I divide by the standard deviation, I raise to the nth power, I compute the mean, and then I multiply times the total number, the percentage of values that I have on that side, where the left-hand side is everything below the mean, the right-hand side is everything above the mean. What I can say is, if that n factor, that which moment I'm looking at is an even moment, then, I just take the left computation, this giant left computation, and I add it to the right computation, and I get the value. If it's odd, I take the left computation, and I add to the right computation, it's the value, and that's what we saw before. But if I also take the absolute value of these two sides, if n is even, this thing is always going to be even, so the absolute value has no effect. But if n is odd, the absolute value preserves the sign. And if I'm on the left-hand side, I'm always below the mean, meaning this part is always negative, meaning this thing is always negative. If I'm above the mean, that means this part is always positive if I'm on the right-hand side. And so what I could say is, for moments where n is odd, like the skew, the third moment, I can compute the right lobe minus the left lobe's moment. For n being even, I can compute the right lobe's moment plus the left moment. What on earth does this mean? Well, think about this. For the skew, what I can do is I can look at all the values below the mean and all the values above the mean. I can compute something like how those values are centered. As a consequence of this little mathematical formalism, what the skew is actually computing is the distance between these two. Think about this. If one of these is a very, very long-tailed distribution, then it's going to pull that moment further and further to the right. If one of these is a very long-tailed distribution to the left, it's going to pull that value very, very far to the left. Because this is a subtraction, that will increase the magnitude of the skew. If they're very tight, it'll decrease the magnitude of the skew. And the skew, remember, is our leanedness. Note that if we pull this thing very far to the right, then this value is going to be more positive or more negative, and that corresponds to which direction this leans. Where the mass of that distribution is in the opposite direction of where it leans. So that's what we saw. It kind of leans left if most of the mass is here, or it leans right if most of the mass is here. But what we can think is the reason why the skew is this leanedness is because it's really looking at these two lobes and computing something in these two lobes and looking at how those two lobes compare to each other, and is factoring into what the asymmetry of those are. Whereas for the kurtosis, oftentimes people talk about the kurtosis as the peakedness. That's not what it is. It's actually the extremity of the deviation. It's actually the sum of where those tails are, the sum of what those two lobes look like. And so the kurtosis is going to be very large if we have an extreme deviation, and it's going to be very small if we don't have an extreme deviation. And this may take you a couple of tries and a couple of looks to really centralize, but I found this to be an incredibly powerful way to get an immediate physical intuition for what the skew and the kurtosis are beyond just the leanedness. Now, as we mentioned, it is the case that the mean, the standard deviation, the variance, and the skew, the variance, the skew, and the kurtosis are not a perfect way to describe a data set, and I did want to share with you something that comes up very often and almost certainly came up in your college stats class, namely Anscombe's quartet. Anscombe's quartet is some hand-picked values that look like this. And these are very different real-world distributions of value. Something is happening very different in each one of these possibilities, each one of these scenarios. Clearly, in one case, the data is kind of here with an outlier here. All the data is over here with an outlier over here. The data is kind of scattered here, or the data has a particular shape. But the mean and the standard deviation for all four of these is identical. However, if we start computing the skew and the kurtosis, then we begin to see that there's a significant difference here. And what we can think is the reason why we might reach for the skew and kurtosis beyond this, how does it lean, or what is the extremity of the deviation, is it immediately gives us a single scalar value to describe this data set that doesn't run into the problem that we see in the Anscombe's quartet, where the mean and the standard deviation, they're great, but they are very limited. You can see how immediately for this distribution, the skew and the kurtosis start to deviate, and how we can now uniquely typify each of these, or at least give some communicative ability of what's going on in each one of these much, much more capably with these four statistics. Briefly, before we move on, I do want to share with you, when we talk about the mean, we're not just talking about arithmetic means. You may sometimes run into things like the geometric mean. Think about this. If you have some ratios, something doubled and something halved, if you compute the regular mean as the sum divided by the length, it's going to say, 1.25. But that's not the case. The average here, in an intuitive sense, is something doubled and something halved should be 1. It got back to 1. And so the geometric mean is a way for us to compute a mean-like measure, but instead of computing that as the sum divided by the length, we're computing this as the product of the values to the power of 1 over the product of the values. And you can see this works out nicely. You can see the average notion here of something doubling and something halving is 1. So this gives us a much better intuition. Similarly, if we were to talk about something that's moving through space at some particular speed. So we have something that moves some distance at 100 meters per second and then moves back that same distance at 20 meters per second. And we're moving 1 kilometer forwards and 1 kilometer back. We can compute the amount of time. We can compute what the average speed is here using our sum divided by our length formulation. And we'll see that we're told, it's 60 meters per second. But that doesn't make sense because clearly we have moved 2 kilometers or 2,000 meters. And it's taken us, that first kilometer, 10 seconds, coming back 50 seconds, 60 seconds. So clearly, our average speed here isn't going to be 60 meters per second. It's actually 33 meters per second, because 2 kilometers in 60 seconds, if I do that division, that's 33 meters per second. Well, this leads us to another formulation, or another way to describe the mean, the harmonic mean. And whereas the mean is the sum of the value divided by the lengths, the harmonic mean is the reciprocal of each of these values divided by the lengths, and then you take the reciprocal of that. Similarly, when we talk about the variance, oftentimes you can see that we're not talking about just one measure for the variance. In the statistics modules in the Python standard library, it can compute the p-variance and the variance. In the .var API in NumPy, you can provide a DDOF parameter. You might wonder, wait, these are very different values. What the heck is p-variance versus variance? And if you try this on a different distribution, you may see that they don't differ that much. For this other distribution here, for this other data set here, they don't really differ that much. And you might wonder why that might be. And the reason is one of these data sets is very small, and one of these data sets is very large. Here is the situation, and it's a very important thing for us to keep in mind. When we're talking about these data sets, are we talking about the data set, knowing everything about the data set, knowing the entirety of the population, or are we talking about observations of what happened in that population? In other words, this data set is very large. It has 50,000 elements in it. If I don't have the ability to observe every 50,000 element, and I can only observe one element, and I can only figure out how to compute the mean on one element, you can see I get a very large range of possible means depending on which element I chose. If I can choose 10 elements, well, I still get a very large range of means because I could choose any 10 elements. I could choose all the 10 elements over here, all the 10 elements over here. I could choose 10 representative elements. Who knows? If I chose 40,000 of the total 50,000 elements, then you can see the means that I'd compute are probably largely clustered around the same point. And if I could choose every element, well, of course, I'm going to always get the same mean. If I were to do the same thing with the variance, one of the problems is the variance is computed using that mean, and so I've lost a degree of freedom. The difference between the population variance and the sample variance, these population statistics and these sample statistics, is this core question. Are you looking at the entire population, or are you looking at some small observation, some window into what you can see of that population? That's what we call the sample variance versus the population variance. And the difference here is merely a corrective factor. It is a heuristic factor. It's called Bessel's correction. And this corrective factor here you can see is just the number of elements divided by the number of elements minus one. If you compute the variance versus the p-variance, you can see the difference here is really just multiplication by this corrective factor. And it's really just a corrective factor to account for the loss of the degree of freedoms because the variance is computed using the means. In other words, and in more formal terms, if you look at the residuals, if you look at each value minus the mean, there's always one less independent residual than there are original observations. But we don't have to go into that in too much detail because I think what's most important is the difference between thinking about this as a sample statistic versus a population statistic. Lastly, you may have seen and spotted in some cases, I've used this Fisher equals true, Fisher equals false for the kurtosis. There are two formulations for the kurtosis. You know what the difference is between the two? One of them is -3, and I actually looked at the code for scipy.stats.kurtosis. The last line of scipy.stats.kurtosis is return values -3 of Fisher, else values. All the difference is, when we talk about the Fisher kurtosis or the Peterson kurtosis, or we set this Fisher equals true or false, is really for a particular given distribution, namely normal distribution, should the Fisher kurtosis be 0 or should it be 3? It's just an additive factor. It really is just you add 3 or you subtract 3. That's the only difference. Having said that,